All right, so this is the video for the first lesson from Unit 2, which is kind of the complete opposite of Unit 1. Unit 1 was a huge unit that covered half the course, 4 chapters, 2 tests. Unit 2 is the opposite. It's 4 lessons, but just 3 sections from the textbook. Very, very short. And so let's just get straight to it. And this first lesson is actually just review of something you hopefully covered in grade 9. And again, you may have not because of the various reasons. But this is a review lesson that builds on some of the key ideas that we'll need for the actual lessons in this short unit. So first, similar figures, as it says, are shapes that are identical except in size. Similar triangles, and this little symbol here is the symbol for similar. So they're equal to each other, but they're not the same size. But the same shape. They're congruent, we say. So similar triangles are triangles that have the exact same angles within, but they differ in size. And so if triangles are similar, then the ratios of their corresponding sides are equal. What does that mean? Well, let's look at it. Here I have 2 triangles, and they're similar. How do I know they're similar? Because I give you that little symbol. So this says triangle ABC, which literally means the triangle with these sides here, ABC, is similar to the triangle DEF. Okay. So really what I want to look at is this phrase that, well, first, what does it mean if they're similar? And what does it mean the ratios of their corresponding sides are equal? Well, what that means is if you look at these 2 triangles, it looks to me like triangle DEF is a bit larger, but they have the same angles. They're the same shape, just one's a bit bigger than the other. So what I can do then is I can say that means sides between these triangles correspond with one another. For example, this side from A to B, right here. I'll just highlight the side in yellow. That side there corresponds with this side here in triangle DEF. In this case, they're both the shortest side. They're not the same length, but they correspond to one another. This side here corresponds to this side here. And this side here corresponds to this side here. All right, so these are what we call corresponding sides. Again, all those sides I kind of colored to kind of show how they correspond. They're not the same length, but they're related to one another. Hopefully that's, you can just kind of see how they're related. And so that means I can say, when I say the ratios of their corresponding sides are equal, if I pick a side, I don't know, I'll look at side AB. So side AB, if I take side AB, so the side I highlighted in yellow on the triangle on the left, and I divide by another side. A ratio means, essentially division. Divided by another side. How about BC? So if I actually gave you those measurements, the side for AB and the side length for BC, if you took those 2 sides and divided them in that order, whatever number you get would be the same if you divided the same corresponding sides in the other triangle. In this case, side DE divided by EF. And there's nothing special about those sides. I just picked some random sides. So it's true for anything. I could say, I don't know, another example is, let's look at the small triangle. I'll say side AC. If I took side AC and divided by AB, okay, if I gave you those measurements and we took the side length of AC and divided by the side length of AB, we'd get some number. That number would be the exact same if I did the same thing in the larger triangle. In this case, side DF divided by DE. So clearly I can keep coming up with different combinations. And I'm not going to keep doing this forever. But that's what I'm showing you here is what this last phrase right here means. If triangles are similar, the ratios of their corresponding sides are equal. And there's so many combinations of sides I could come up with here. And I just showed 2 examples. So now an important question is this: how is this of any use? Well, let's see. Here are 2 triangles that are similar. And I know they're similar because of this phrase right here, right at the top. It says triangle GHI is similar to JKL. That means these 2 triangles are the same shape, but one is larger than the other. But that means they have all the same angles. Now in this case, the hardest part is probably figuring out which sides are corresponding to one another. So for example, let's look at this side right here that's 5 centimeters, GH. Which side corresponds to that? Well, the way I would look at it is GH is clearly the shortest side, so it must correspond to the shortest side in this larger triangle. So GH must correspond to KJ, which notice we don't know what the length of that is. Okay, Well, how else do these sides correspond? Because it's hard, because sometimes the triangles are rotated around and whatnot. Well, one thing that's sometimes helpful is to kind of look at these angles here. Angle G and angle H and angle I, these three angles are all different. At least I assume they're all different because it doesn't say they're the same. So I'll put a little 1 tick, 2 ticks, 3 ticks. Okay, I have 3 angles. So how do they correspond to the triangle KJL? One thing we need to realize is that this triangle here has actually been rotated. So angle G corresponds to angle K. They're the same angle. Angle H corresponds to angle J. That's the same angle. And probably the most obvious is that angle I corresponds to angle L. So once I know how these angles correspond, then I can say, okay, just kind of looking at these, I know this 12 centimeter side must correspond to this 20 centimeter side. And therefore, there's only one side left. This blank side in the triangle on the left must correspond to 30 centimeters, something on the right. And so if these two triangles are aligned the same way, it's really obvious to see how the sides correspond. If they're not, like this, it's probably not so obvious. And you have to look really carefully to see how the angles compare. Well, that's it. The hardest part of the question is now done. So what I want to do now is find the lengths of HI, which is highlighted in green on the left, and find the length of KJ, which is highlighted in yellow on the right. Just pick one. I'll do HI first. Actually, I'll do KJ first. So if I look here, how can I find the length of KJ? Well, for example, I want to figure out that side there. I need to make a ratio using that side. So I'm going to say KJ over 20. So the unknown side divided by 20 on the triangle on the right. Whatever we know, that ratio must equal to the corresponding sides in the smaller triangle. In the smaller triangle, the side that corresponds with KJ is 5. You know, if I've highlighted everything, it gets a lot more obvious. The side that corresponds with 20 is 12. And so now notice I have an equation with two ratios that equal each other and one unknown. So I can solve this in many different ways. One thing you may have learned about is cross-multiplying, and cross-multiplying is a really convenient way to solve something like this really quickly. And cross-multiplying always works when you have two ratios that equal each other with a single unknown, two fractions that equal each other, if there's nothing else. And so in this case, and again, you may know all this already, you may know none of this already. If I want to figure out the side of that angle, the length of that missing side, KJ, first what I do is I look at these three values I know, and I find the two values that are diagonally across from each other. In this case, 5 times 20. And I'm going to take those two numbers and multiply them by each other. So I'm going to go 20 times 5. And then, there's always one number left. So whenever there's one unknown, there's two that are diagonally across from each other. I multiply those together. And then there's one number I haven't used yet. In this case, that's the 12. I take whatever I did before and I divide by 12. And that there will always equal the missing number. In this case, KJ. Always, always, always. So in this case, I get 100 divided by 12. Which is about 8.3. So I know that KJ equals about 8.3 centimeters. And what I just did here, this is called cross multiplication. And which is what I mentioned here about multiply the two numbers that are diagonally across from each other and divide by what's left. That'll always, always, always work to find any missing value in a pair of ratios like this that equal one another. So it's quite useful for things like this because it's so quick. In this case, 20 times 5 or 5 times 20 divided by 12, there's your missing number. So that side KJ in the triangle on the right is 8.3. And most of my work here was really, once I set up the triangles, was just me talking. But the actual work is extremely quick. Okay, I also want to find side HI. So that's this side right here. Same idea. I want to set up a couple fractions. I have lots of choices. I'll start with HI. HI divided by, 12. So in the triangle on the left, green divided by 12. I have other choices. I'll just stick with this. Once I have this set up, and I need to be careful how I set up the other. The sides have to correspond. So what corresponds to HI? 30 centimeters. What corresponds to the 12? 20. Again, I've highlighted everything deliberately, so that should make that much more obvious. Now to cross multiply, I find the two numbers that are diagonally across from each other. So 12 times 30. And then I divide by what number's left? 20. So whatever 12 times 30 is, and then I divide by 20, that will tell me HI. And I get 18. So HI equals 18 centimeters exactly. Now there's other options about how you can approach this. Again, to go from here to here, what you're really doing when we're cross multiplying is we're really multiplying both sides by the common denominators and dividing out. This is faster. There's other options as well. In the end though, this cross multiplying always works, and it's always nice and quick for equations like this, so it is something I generally recommend. All right, so notice I found these two measurements of these two unknown sides by looking at how these two triangles were proportionally related to one another. All right, so one more example, and this leads into the next lesson. So I have a triangle here with a right triangle with a side of 5 centimeters and an angle of 20 degrees. Okay, some terminology I want us to remember about a right triangle. The hypotenuse is always the longest side. So this side right here on an angle is the hypotenuse. It's also always the side opposite to the right angle, the 90 degrees, always. So what does it say here? For any right triangle that has a 20-degree angle, the ratio of the side opposite to 20 degrees divided by the side adjacent to 20 degrees is approximately 0.364. Okay, what does that mean? Well, the side opposite to 20 degrees is what I've highlighted in yellow. Literally, here's my 20-degree angle. That side over there is opposite from it. And that's what we say. That phrase opposite means it's the side that is across from it. So this side right here we say is opposite to 20 degrees. And the phrase adjacent to 20 degrees, that's this side right here. That's the side that's right beside, but not the hypotenuse. So we say this is adjacent. And those phrases we're going to hear lots: opposite, adjacent, and hypotenuse. Okay, opposite means across from an angle. Adjacent means right beside, but not the hypotenuse. The hypotenuse I've labeled in red. Hypotenuse is a phrase I hope sounds familiar. That said, how can I use these terms to answer the question? I said the ratio of the side opposite to 20 degrees divided by the side adjacent to 20 degrees is approximately 0.364. And I want to find the height of the rectangle. Well, the height of the rectangle, triangle. The height of this triangle is the same as this side in blue. It's the same as the side adjacent to 20 degrees. That's the height of this triangle. So I'm trying to find the length of that side in blue. I'm trying to find the length of the side that's adjacent to 20 degrees. So how do I do that? Well, let's start by writing down what it says. If I take the side length opposite to 20 degrees, so 5 centimeters, and I divide by the side adjacent to 20, well, I don't know what that is. I'll call it x. Right, but that's what it says here. The ratio of the side opposite to 20 divided by the side adjacent to 20 is approximately, so this equals approximately 0.364. Right, is approximately 0.364. So I've just now taken that information that was told to us in the question, and I've written as a quick little equation. So now find the height, find x. How can I do this? I can solve this by cross multiplying, actually, if I just look at this 0.364 and make it look like a fraction. Write it over 1. And now I can cross multiply. First I'd find the two numbers that are diagonally across from each other, which is 5 times 1, which is 5, and then divide by what's left. In this case, 5 divided by 0.364. Clearly a calculator is handy here, and that will tell you x. And x comes to be about 13.7, in this case, centimeters. So notice, like pretty much everything we've done today, if anything has been challenging, and I expect some parts are, it's not about the actual calculations, it's about setting these things up. And there's some terminology here. Chances are opposite and adjacent, these phrases are kind of new. Hypotenuse is definitely not new. That goes back to the Pythagorean theorem. But really, the calculations are really, really quick. And that'll be sort of a theme you'll notice for this entire short unit. There's very few calculations, and they're all quick. And so with a bit of practice, we can tend to get this down pretty good. However, there are a fair amount of perhaps new terms. Really, the two key ones today are opposite and adjacent that we're going to start hearing a lot. Okay, so that's it. This lesson doesn't have any homework. It's review, and it's meant to just set up the next lesson. So if anything, if you're unsure, I would just watch it again if you're unsure, but there's no homework for this lesson.